When I was walking through the college with the window there, and I saw them going to physics lab. And what I've seen pretty well. I can tell they're moving to they just have like, they had something set up to like, I don't know, I didn't know what they were doing exactly, it looked fun. So they were like setting something up, producing that motion. A little more fun than what we have to do the next structure function lab. Dissect the sheet.
Even so, some of them were gross, but
Yeah.
I liked it.
Any of the dissections is going to be something.
I enjoyed kidney dissection.
Is it something like? Is only one person trying to have to do it?
So basically 4 runs.
Oh. So one brain.
No, 2 lane for each group.
Oh, yeah.
The blame was for social function 1. Okay, this is hard.
Oh, yes. Yeah, I'm gonna have my partner do that, and I'm just gonna take notes.
Kidney.
Oh, man.
I like kidney. It's working. I
did that in high school.
You did?
Yeah. So like I still have done my time. I don't really do it anymore. So I give somebody else a chance. Sorry for this. Wait, you mentioned oh, yeah, yeah. Did you like sell your something? Oh, okay. Yeah, that's true. Oh, yeah. I don't see you as something. What was just the one? Oh.
Not as good as the last.
It's like, yeah, not as good as the last one, but at the same time, I keep thinking, it's the last time the version test, it's gonna be.
Pretty straightforward.
In the last one, there were so many questions where it was like, I knew the answer just because 3 of the answers were completely out there. I was talking to Charlotte about it, and she was like, I feel like if you wrote the right question, just go back on the test or different questions. And it'd be, yeah. I was like, pretty much the license was like that. That's a lobster.
Chapter has studied. Yeah. Yeah. I did not mean to slam that. Oh.
That was not my intention at all. I guess I'm just trying to wake us all up on Tuesday morning.
Okay.
Any questions for me before I get started into today's material?
I don't know about that homework, but I can just read after.
Okay. Anything else? I will be posting homework over what we discussed yesterday and what I'm discussing today. Sometime today. So that'll be due next Monday. Okay. Organize myself. Okay, so yesterday we started talking about the amines Today, we're going to finish up amines and we're going to get into carboxylic acids and their derivatives. Basically, what we need to do is discuss the reactions of amines and then how to name the ammonium ions that are formed from salts. And then once we've discussed that, we'll get into chapter 17, which is the carboxylic acids. So, it's coming around. Yes.
It says quiz 6 on active is due in 2 hours.
That's a mistake. It should be due at 11:59 p.m.
Okay.
So I need. So. What I can do is let me change that so I don't forget.
Yes, sorry.
Here we go. Okay. Now that's taken care of. It's now due in 16 hours. Any other comments or questions? Okay, so what we're going to do is we're going to talk about the reactions of amines. And depending upon who you had, you may actually already know this information because it's essentially information that is often gone over in Gen Chem for health sciences. So basically, let's say we have the reaction of ethylamine and we place that ethylamine in water. The ethylamine is going to act as a base and the water is going to act as an acid. The water is going to donate a hydrogen to the base. And what you're going to generate is you're going to generate CH3, CH2, NH3 plus. and hydroxide. The CH3, CH2NH3 plus is the conjugate acid. And the OH minus is the conjugate base. Now, ethylamine is a weak base. And because it is a weak base, we set up an equilibrium between these two processes. Does this look familiar? That is the reaction for your amines. The amine goes to make an ammonium ion. And it doesn't matter what amine we're looking at. We could look at aniline. If you react aniline in water, the aniline is going to act as a weak base. And the water is going to act as an acid. It's going to set up an equilibrium where the acid donates a proton to the weak base. And what you wind up forming is a salt. Or, well, is a ammonium ion. Okay. Now, because this is weak base, weak acid interaction, you could also take our CH3, CH2, NH2 and react it with hydronium. Again, the hydronium acting as an acid and the ethylamine acting as a base. The water donates its proton. Well, the hydronium donates its proton. And so what you wind up forming is, again, you wind up forming the ammonium ion plus, in this case, neutral water. So I gave you specific examples, but one of the things that we discussed yesterday is that instead of memorizing specific examples, you need to understand what is the concept. And the concept here is that if you place an amine in water or in a weak acid like a hydronium situation, you will get an ammonium salt or ammonium ion. If you place an amine in water or in the presence of a weak acid, a hydronium ion, you will get the ammonium ion. That is the general reaction. Now, again, these ammonium ions are conjugate acids. So if you have an ammonium ion, such as CH3CH2NH3 plus, and you place it in the presence of hydroxide, you're going to have the proton, it's going to act as an acid. And you're going to get the ammonium right back out, or the amine, excuse me. You're going to get the amine right back out. You got to remember what equilibrium means. So, key points. To reactions. The neutral amine reacts as a weak base. Therefore, it accepts a proton from water, hydronium, or technically any other weak acid. The result is the formation of an ammonium ion because we are working with weak substances. The reaction is at equilibrium. The key to this statement here is I started with the neutral amine. If I start with the ammonium ion, they will react as a weak acid. Therefore, they will donate the proton and form the amine as a product. Again, this reaction is at equilibrium. Because we're dealing with weak materials. So again, the key here is what I started with. Does that help tie down the reaction type for the amine? Instead of looking at specific reactions, we looked at what is the concept. The concept is these reactions set up equilibriums between the ammonium ion and the amine.
Is there another weak acid that we could see?
I mean, technically any weak acid, anything that has a proton, like an alcohol, can be a weak acid. We will see that when we get to the carboxylic acids, the amine will react with those carboxylic acids. So just in general, I wanted to put it up there because we're going to get there, but did that help some in nailing down the reaction? Well, then let's look at something. Let's look at this reaction, and I want you to predict the products. What will be the products of that reaction? If you drew the pyrrolidine with 2 hydrogens and made it an ammonium ion, then you would be correct. With the other product being hydroxide. Let's look at another example. Let's take and react this with an HBr. What is HBr, by the way? It's an acid. It's hydrobromic acid. What will be the products? If you added a hydrogen, it doesn't have to look just like what I just drew, but if you added a hydrogen to the amine and made it a ammonium ion, then you are correct. It all depends upon whether the substance you're working with is weak. In this particular case, hydrobromic acid was a strong acid.
Are we going to need to know?
You won't need to know that piece. Except with water. Let's look at one more. I'll give you one part of it. That way you don't have to worry about it. What's the rest of the story? If you created the amine from the ammonium ion and then water is what the result would be. Yes.
Would it be one of the things that we have to put in order to get it right?
No, no. You can leave the Na off. I'm wondering, can you get the amine to the ammonium? So again, your entire thing was if you started with the amine, that's a base. It accepts a proton, makes ammonium. If you started with the ammonium, that's an acid. It gives off a proton to make the amine. So that goes back to what I wrote up here about the key points. I'm trying real hard to answer that question that you had yesterday. Okay. Let's talk about naming the ammonium ion. Okay. If you have a alkylamine, then you're going to replace amine with the words ammonium ion. So earlier I called this ethylamine. When we made the ion by adding a hydrogen to it, this now becomes ethyl ammonium ion. Now, for heterocyclic amines, which basically means that the nitrogen is in the ring, then the E of the name is replaced with ium ion. So for example, this is pyridine. So if I make the ion of this, this would be pyridinium ion. Okay, so some more memory work. These heterocyclic amines, if you look at page 509, table 16.1, those need to be memorized. So again, the keys to this you've got to know whether it's an alkylamine or whether it's a heterocyclic amine to know exactly how you're going to name the ion that it produces. Okay, so we've talked about the reactions, we've talked about how to name the product. The other thing that we need to talk about is the strength of base. How strong is the base? Or in other words, its basicity. Your non-aromatic amines are going to make for a stronger base than will ammonia. So your amines, folks, are stronger than ammonia. Ethylamine is stronger than ammonia. Propylamine is stronger than ammonia. Your non-aromatic amines are stronger than ammonia. But your aromatic amines such as pyridine are going to be weaker than ammonia. You should know that order of basicity. Okay. Any questions about the reactions of an amine or the corresponding ammonium ion? Any questions about how to name the amine or the corresponding ammonium ion? Any questions about the relative strength of amines and the corresponding of the amines relative to ammonia? The last thing in chapter 16 that we will talk about are amine salts. Okay, first things first, we're going back to Gen Chem for Health Sciences for a minute. A salt is an ionic compound that contains a cation and an anion. A cation is a positively charged ion. Whereas an anion is a negatively charged ion. Cations and anions cannot exist without each other. Basically, folks, you can't have cation just floating around doing its thing unless there's an anion somewhere floating around doing its thing. You just can't have one without the other. They don't exist separate. You can't have a solution that's nothing but cations. It won't happen. So when we get to an amine salt will be an ammonium cation combined with an anion. Okay, so far, so good? Now, the way we write this is, for example, let's take our ethylamine, just because it's a simple one for the moment. We would have, so this, if you'll recall, is ethylamine. If we were to react our ethylamine with, say, hydrochloric acid, the acid is going to donate its proton to get the ethyl ammonium ion. And if we're talking about a reaction, we frequently write the chloride as separate. So we're going back to what we just discussed. Now, these two things, however, are going to come together to make a salt. Whoops, not yet. And you just write the ions in close proximity when you're writing the formula for a salt. Sometimes you'll see it written with the plus sign over the nitrogen. Sometimes you'll just see it written with the plus sign to the right of the amine. But in general, it's on the plus is on the nitrogen in the amine. Now to name this salt, back when you were in Gen Chem for Health Sciences, you talked about sodium chloride, sodium ion, chloride ion. To name the salt, you combine the two. To name the salt, we're going to combine the two ions. So this salt is called ethyl ammonium chloride. That's with all the salts of ammonium. All ammonium salts, you simply combine the name of the cation with the name of the anion, leaving off the word ions. Cations are always listed first, so the positive charge always gets listed first. Let's look at a couple of examples. Let's draw the structure. For in butyl, or let's see, no, it'd be butyl. In diethyl butyl ammonium bromide. Okay, I'm breaking this down. I got butyl ammonium as the base, as the parent. So that means that's the CH3, CH2, CH2, CH2. And because it's an ammonium ion, I'll come back to that piece, but I'll put, for now, I'm going to put the N. That takes care of the butylamine. Now the NN diethyl means that it's CH2, CH3 attached, and there are two of them. And because it is an ammonium ion, that means that it is got to be a plus charge. So there has to be a hydrogen there. And then the bromide. Let's look at another example. Tetrabutyl ammonium hydroxide. Well, the first thing I notice is this term ammonium, which means it's got a nitrogen. But this one's a tetrabutyl. So in other words, on that nitrogen, whoops, there has to be 4 butyl groups. Because there are 4 groups attached to the nitrogen, that nitrogen is a positive charge, which is counterbalanced by hydroxide, which is a negative charge. So all of that combined would be tetrabutyl ammonium hydroxide. NN only occurs if you have, if you go back to our original discussion, you only have to use NN if, or the N, if the alkyl substituents are different. So it wasn't required here because the alkyl substituents were all the same.
Question. Why would it be like the yeah, this terpene I figured out.
Okay.
Is the hydroxide actually a part of that molecule?
It is, but Ionic compounds don't get bonds. They don't, you don't see a bond drawn. You just see them in proximity together.
Okay, but close enough that they probably kind of like float around.
Yes.
Oh.
It's kind of, ionic bonds are like magnets. And when you pull the magnets together, you don't actually get a bond in between. It's just the attraction.
Okay.
So as long as they're in close proximity, it says there's an attraction between them.
So the tetra represents like 4?
Yes.
Okay.
Tetra is 4. Di is 2, tri is 3, tetra is 4.
And where's the positive charge on the antiatom again?
Anytime. So we could go back to Lewis dot structures. And when you make a 4th bond, the nitrogen no longer has a lone pair. And because it no longer has a lone pair, it winds up getting a positive charge. So just to keep it simplified without us getting into Lewis structures and formal charges and stuff like that, which is what we would need to go into. Anytime there's 4 bonds on a nitrogen, it's going to be positively charged. So again, without getting into Lewis dot structures and without getting into formal charge, if there are 4 bonds on a nitrogen, it's positive. If there are only 3 bonds to the nitrogen, then it's neutral. Questions? I like questions. This is good. Okay, any more questions about amines? Okay, folks. So far, we have talked about alkanes, which are the baseline for everything. Everything has some alkane involved. We talked about alkenes. And when we talked about alkenes, we brought in the topic of saturated and unsaturated, where if it has a double bond, it's unsaturated, or if it has a triple bond, it's unsaturated. Then we moved into alcohols, sulfur-containing compounds, and halogen-containing compounds. And with the alcohols, we talked about primary, secondary, tertiary alcohols. We are going to start seeing alcohols again in our next chapter. With the sulfur compounds, we're mainly going to see once we start making protein chains from amino acids. After alcohols and the halogen compounds, we briefly discussed aldehydes and ketones. A primary alcohol can be oxidized to an aldehyde if you're gentle. But if you have excess oxidizing reactant, a primary alcohol is going to go all the way to the carboxylic acid. Whereas a secondary alcohol will go to a ketone. And tertiary alcohols don't react. At that point, I introduced the carbonyl group. We also talked about, with alcohols, the formation of hemiacetals and acetals because they are directly related to sugars. Hemiketals and ketals because, again, they're directly related to sugars. Then we talked about the amines. And an amine is going to be a nitrogen containing compound. Now, we move on to carboxylic acids and their derivatives. This chapter takes, number one, carboxylic acids. We've got to talk about those. Then we're going to talk about carboxylic acids when they react with an alcohol to form ester bonds. That is going to be important when we talk about lipid formation. We're also going to talk about how carboxylic acids react with amines to form amide bonds. And amide bonds are the base formation of proteins. So this chapter really is starting to move into the concepts that we are going to use quite a bit in the last portion of this semester. Most of what we've been doing has been building up to this. Now we're getting into the nitty-gritty. But first, we got to get through carboxylic acids, and then we can get into the biochemical reactions. So, a carboxylic acid is going to be a carbonyl group attached to an OH. They are the starting point for ester formation and amide formation, which again, ester formation is what occurs in lipid formation. Amide formation is what occurs in protein formation. These are polar compounds. That can hydrogen bond. And they have the strong OH group associated with hydrogen bonding. One of the derivatives for carboxylic acid is going to be an ester. Because of the carbonyl, esters are still polar compounds. But their strongest force is the dipole-dipole interaction. The next thing we have is another derivative. Which can be a primary amine or primary amide. A primary amide is going to be a polar compound. It can hydrogen bond. But it has the weaker NH bonds compared to the OH. You can have a secondary amide which is a polar compound. And it still has the ability to hydrogen bond. But is weaker than a primary amide due to fewer hydrogens on the nitrogen. Finally, you can have a tertiary amide which is still going to be a polar compound, but its main force will be that of dipole-dipole interactions. These concepts are going to play into the physical properties like melting points and boiling points as we progress. Because if they have, number one, if they have hydrogen bonding capability, you can expect them to be a higher melting point and boiling point than if they do not. So out of these, the tertiary amides and the esters, they're going to have the lower melting points and boiling points because they have the weaker forces. The carboxylic acid probably has the highest melting point and boiling point because it not only has hydrogen bonding capability, but it specifically has that OH group available, which means it's got a stronger the intermolecular forces will be stronger due to the difference in electronegativities of the O and the H. Then you're going to probably, after the carboxylic acid, you'll probably have the primary amide because it has greater hydrogen bonding capability, followed by the secondary amide. And all of these are going to have a much higher melting point and boiling point than alkanes, which have simply London dispersion forces. Since the next big thing is to get into the general reaction, and it is the general reaction, and then getting into specifics about your carboxylic acids and about your esters and about your amides, instead of trying to start that topic now, I'm going to quit class now, and we'll pick up with all of the reactions and the naming of carboxylic acids, esters, and amides on Thursday.
In the progression of it would be ester, tertiary amide, secondary amide, primary amide,
it's probably more like tertiary amide is the weakest, followed by ester, followed by secondary, then primary, then carboxylic acid. And the reason for that is because of the polarity of that oxygen in the ester. It's stronger than that of the nitrogen.